And then we're practically done the chapter. All right, so moving on to section 7.10. So we finished section 7.9, and here we are. And now we're going to look at other substrates. And so really, this section deals with other good leaving groups. So far, the leaving groups that we saw that were good, so good leaving groups were iodide, bromide, chloride, and water, really. I mean, and why are those good leaving groups? Because they're the conjugate bases of strong acids, right? Iodide is the conjugate base of HI. Bromide is the conjugate base of HBr. Chloride is the conjugate base of HCl. And water is the conjugate base of hydronium. And so now we're going to learn some more good leaving groups. And so, of course, they must be the conjugate bases of other strong acids. So it says here there's a variety of alternatives to alkyl halides for substitution and elimination reactions, such as alkyl sulfonates. So we're going to look at a bunch of things here that we call alkyl sulfonates. And what they have in common is that they all have some kind of alkyl group, and then they have SO3 minus, okay? So you notice that every single one of these has an R group, right? You have an R group here, and then an R group here, and then you have some kind of SO3. And so, of course, if that functions as a leaving group, it'll leave as an anion, as SO3 minus. All right. So we see the names of these leaving groups. We have the mesylate, which we abbreviate OMS. So that's the first one here. So OMS is the mesylate. Mesylate actually stands for methane sulfonyl. So methane sulfonyl or mesylate. The next one is a tosylate. So we abbreviate that OTS. And tosylate stands for toluene sulfonyl. So toluene sulfonyl. And the last one is a triflate. And triflate we abbreviate ROTF. And so that stands for, triflate stands for trifluoromethane sulfonyl, if you can believe it, stands for all of that. So now, besides these good leaving groups that I had written in blue before, now we're also going to add to it, where's my blue pen? OMS, okay, minus, right? What else? Maybe I'll write them the same way as they're written there. So we'll put, right, son of a gun. The mesylate will be a good leaving group. The tosylate will be a good leaving group, and the triflate. Okay, those will all be new good leaving groups that we're going to discover in here. And the one we're going to talk about the most is going to be the tosylate. So the tosylate will come up the most. All right, so why would these things be good leaving groups? Well, you can probably guess why, because you saw that good leaving groups are weak bases, right? They're the conjugate base of strong acids, so therefore they're really weak bases. And how do you have a weak base? Well, you have to have something that has a negative charge that has to be very stable. And you can see that the negative charge on an alkyl sulfonate is resonance stabilized, right? We have 3 resonance structures that contribute to the hybrid here. Also, if you look at the pKa's of their conjugate acids, you get methane sulfonic acid, toluene sulfonic acid, and trifluoromethane sulfonic acid. What do you notice about all of their pKa values? Their pKa's are all less than 0. And we said that a pKa less than 0 meant it was a strong acid. If you look at the 3 of these, could anybody answer this? Which one of these would make the best leaving group? Would it be the triflate, the tosylate, or the mesylate? It's the triflate, isn't it, right? This one would be the best leaving group. So best leaving group would be the OTF group, right? Because its conjugate acid is the strongest of all. In fact, you're probably looking at this and going, man, this is stronger than sulfuric acid. And you're absolutely right. It is stronger than sulfuric acid. It is more acidic than sulfuric acid. But if you remembered in the last slide, I said the one that we use the most is this one, paratoluene sulfonic acid. The reason why is this is a solid at room temperature. This molecule is a solid, and so it's much easier to work with. You can just weigh it out on a balance. So how do you make a sulfonate? You make it from the corresponding alcohol, and then you also need pyridine to function as a base to do the proton transfer that you see here in the second step. So the first step is essentially just a nucleophilic attack. So you get a nucleophilic attack and a loss of leaving group. And then, so this would be nucleophilic attack. And then you get a proton transfer here. And then you get a proton transfer in the second step. So it says here that we're just strapping the TS group on the oxygen of the alcohol, and so there's no change in the stereochemistry of the carbon oxygen bond.